might have a lot to get through. This is the last week of the semester. Welcome to December. Almost come to the end of the semester, and I feel like we just started. So, sure you've seen this before. There's a homework that's due on Thursday, and if you've not started, maybe now might be a good time. It could take some time to run. I saw some conversations on Canvas about how long this is taking to run and how painful it is. So it could be that you haven't started yet. Maybe it's time to start. Are there any questions on that you'd like me to talk about in class about homework?
Yeah, value is supposed to be really, really low.
How low is really low?
36.
Yeah, I did a trial run. I got like 40. Yeah, but takes a bit of effort. But that's with this VMs. I expect that if you use these feature transformations and stuff, you might get a little more. But it's not going to be satisfyingly huge. Are other people seeing these kinds of numbers like 36, 35? Yeah.
36 only when everything's labeled negative.
You see 36 only when everything's labeled negative.
That's I get the best when I just label everything negative.
Oh, okay, I think there's a bug here. How do you measure that bug?
So it's oh wait, yeah. No, label everything when it's labeling everything positive.
When you label everything positive. You know what, we can do this math very quickly to make sure that so can someone tell me what's the number of positive examples? What's the size of the test set? 10,000. So number of examples is 10,000. How many of them are positive?
3,200.
How many?
About 200.
It's 2208.
22.
Okay, so
It's not.
number of
It's like about 2,000.
okay, let's just make it 2 something like that. And let's say you label everything positive. So number of correct is, of course, you got everything right. Right, if you label everything positive. And then number of, so the precision is number correct divided by number predicted, which is something like that. Now recall number correct by no. Right? So
True positive is false negative, so
Yeah. And
Sorry?
above we have
yeah, like the bottom is like correct over like true positive plus false negatives.
plus false. Yeah, in this case there are no false negatives because I didn't predict any negatives. Yes. So can someone do the math for me? It's okay, that's as far as I can go. Can someone tell me what this is? 0.36?
Yeah, okay.
Is that, can someone verify this? Yeah? Okay, so the bottom line here is, it seems like you need not have trained the classifier to get an F1 of 0.36. I did actually check when I trained my SVM, and it did not predict everything as negative, as the same label, whatever it might be. So I suspect what's happening is okay. here's something I would suggest you try just as a sanity check. And if you do this, you mentioned this in your report. Instead of cross-validating for F1, try cross-validating for accuracy as you always did. See what happens. You should not. I mean, you don't need a classifier to get this result, right? So try cross-validating for accuracy. Now that I think about it, in my code, I forgot to swap that out. So I may have just done cross-validation for accuracy, and so see if that changes anything. The other thing to worry about, in addition to printing just F1, you can also try to print the precision and the recall. Because if you basically get a recall of 100%, that seems suspicious. One other possibility is you can, let me just make all of this smaller. Another possibility is you could try to favor precision. See, it seems like here recall is easy, precision is difficult. Recall is easy because you predict everything. You can get 100% recall without doing much work. So you want to favor precision in some way, so you could try cross-validating for precision, for example. So this is the part of machine learning that may start sounding like it's just hacking around until something works. And of course, we don't call it that; we call that data engineering. And it turns out this is going to be something that you will end up doing a lot of in the wild, because when someone gives you a data set and says, go learn, what can you assume about it? What do you know about it without actually trying things? And this is a part of exploration that makes applied machine learning slightly a bit of an experimental science, which is why you need to start, all those things that you learn whenever you learn high school chemistry or I don't know, my last chemistry was high school. Keeping track of good experimental practice, all of those things apply here because it's not just writing code. It's making hypotheses about, in this case, hypotheses, and seeing whether they work. So some ideas that you could try just to see if it works for this homework. Try cross-validating for accuracy, see if that breaks anything. Try cross-validating for precision, see if that changes anything, because you really want to get high precision. Now, the risk that you run when you cross-validate for precision, I usually don't like doing that, because what ends up happening is it can end up predicting the number of predicted positives is 0. So it is so afraid of predicting anything as positive that it picks a hyperparameter that it doesn't want to predict anything as positive. This denominator becomes 0, and the convention is when the denominator of that is 0. I mean, of course, if the number of predicted positive is 0, the number of correct positive is also 0. What that means is among all the 0 positives that it predicted, all of them are right. So the precision is 100%. So you get 100% precision and 0 recall. So that basically seems like it's 50% F1, which is also not very good. So you have to somehow balance yourself against both of these things. And one way of avoiding that is actually not just reporting precision and recall in F1, but also not just reporting F1, but also reporting precision and recall. Don't let one number kind of fool you about your classifier. You can't just let the performance of your classifier be distilled into just one number. You need to look into more. And I'll be talking more about this kind of analysis also in the next lecture, because all of that is the next lecture will be all about practical advice on, don't make the same mistakes I made kind of stuff. Yes.
Do you take any particular priority, or is it just
All these ideas?
no precision recall?
Oh, it depends on the application. It depends on the application. Imagine, so I'll give you I'll try to come up with examples where both precision is independently, like precision is important in one and recall is important in another. Imagine your classifier is predicting whether a patient has some disease. And if you believe the classifier, then the patient has to undergo chemotherapy, let's say, something very invasive. then you really want your classifier to be right. And I think in that case, precision matters. Maybe, I don't know. Maybe I started that example without thinking it through. But I think in that case, one of them may matter more than the other. You can come up with examples where the cost of mispredicting positives and negatives are disproportionate. So, depending on which one is more important, precision and recall may be more. And similarly, the cost of missing one may be important. Let's say that you have a needle in a haystack problem, where there is some information in a big collection and your classifier has to find it, but it exists only once, which means you care about recall. You need to find that information. It doesn't matter how much, like search engines have that. Search engines have to trade off between precision and recall in interesting ways because the internet contains, let's assume the internet contains everything we need to know. But it only gets to select the top one link or the top 10 links. So you want the precision at top 10 among them to be high. You don't care about the precision later on. So there is a preference base that's imposed often by the application. It's hard to tell upfront. So it's really that's where the domain becomes important. That's where the task definition becomes important. Where you have to think about is it okay if the classifier occasionally misses a few things, but when it says something you believe it. That means precision should be high. Is it okay if the classifier occasionally keeps saying, giving garbage as long as it does not miss anything? In which case, recall is important. F1 is like a way of saying, I don't know much. I'm just going to ask for both. Or I'm going to weigh them equally. If you're interested, look up something called the F beta, or generally it's also called the F score, which is a way of trading off precision and recall using a single number by weighting. The F score is defined to be 2 precision recall divided by P plus R, right? Instead, F beta, if I remember right, is, so this is F1. F beta is 1 plus beta times R divided by, I think, P plus beta R. I don't remember which side the beta attaches. But what happens here is if beta is high, then it favors recall. If beta is low, it favors precision. So you can kind of cross-validate for F beta. And you have to check, look up which side the beta attaches. I always have to look it up. I never remember. But yeah, so this is just, you have to try things out. And I have proof of proof by existence that in this data set, I was able to achieve F1 of some 40% without predicting everything as positive. But that doesn't mean that, I did exactly the same things that I asked you to do. In particular, I'm fairly certain I cross-validated for accuracy. But you can try it out. Yeah.
So with like low C values,
Right.
From what I understand, it's going to eventually to the point if your C value is below 1 that you're always guessing negative 1 because if you sum up the weight vector, it's always going to be like around 0. It's definitely going to be less than 1, which will give it the tag, or it'll give it the weight negative 1 in the prediction. And I kind of justify this myself by that first term in the update basically makes the weight vector a little bit smaller, right? Or
you mean the shrinkage?
Right. Shrinkage, and then the regularization term.
That's the shrinkage is from the regularizer, but you're talking about the last term.
The loss term, sorry, yes. When the C is low, it basically can't add a lot.
But
so it's only taking away, right?
So when the C is low, hold on. Let's just you said a lot, so let me take it apart, or take the argument apart. Let's see. When the C is low, you're right. The impact of the loss is not that high at any point of time during learning. And that kind of works intuitively. That means that when the C is low, it's okay if the classifier does not fit the data, because it does not strive to overfit the data. So that's right. However, the shrinkage never changes the sign of the classifier. So it's only multiplying by positive numbers, so it never changes the sign. So if you get all, so the fact that you have the weights shrinking cannot justify that all your weights are negative. Right? If all your weights are negative, they must have started off as negative somehow, or they must have hit some point of being negative before they start shrinking. So I don't think that should happen. I don't think that all your weights should be negative.
Well, right, but sorry, not all the weights are negative, but it's always predicting negative because the weights are approaching. The weight is approaching zero.
Okay.
Right, because it's and so then no matter what, if we look at the example set, generally the features are over one, and so if you were to sum all these features and make a prediction, it's always going to be less than one, meaning that your label will always be negative.
Okay, I think I found your error. Your prediction is not comparing to 1. Your prediction should be compared to 0. At prediction time, it doesn't.
For SVM.
Yeah, it doesn't matter if it's SVM or anything. This is okay. This is a common mistake. So let me move to another slide. And okay, so prediction. For SVM is always the sign of W transpose X. I'm assuming there's a bias inside W. Or equivalently, if W transpose X is greater than or equal to 0, predict plus 1, else predict minus 1. Now, this is the same prediction rule for SVM, for logistic regression, for perceptron, it doesn't matter. The comparison to 1 only happens during training. And this is like your margin perceptron. Like, what happens during training is you compare to 1. You want to introduce this margin of safety during training, but at prediction you still compare to 0, and that way there's a gap between 0 and 1 that is your margin. That's your, that's the, in some sense, the margin of safety between training and prediction. Hold on. Does that?
Yeah.
Okay. Yes. Yeah.
So why do you think that we should still undertake with
With
C equals 1? It's very possible to undertake.
it all. So if I understood the concern, all the predictions were negative, right? Now, here's the situation. If instead of this, what he had done was instead of 0, it had been 1. Then, of course, all the predictions. There's a higher chance that all predictions are negative because you have to cross a higher threshold. And in fact, I don't know why, but I found that the weights tend to be rather small in a lot of problems because of the regularizer, I guess. But if the weights are all small, then crossing the threshold of 1 is going to be very high. So it will end up predicting all negative 1s. But if you compare to 0, it may not make. There will be definitely the set of examples where the score is more than 0 is definitely more than the set of examples where the score is more than 1. Yeah. So I think that's what's happening. Yes, you first and then you. Yeah.
As a follow-up question, if I set the threshold instead of 0, if I set it to -1, I found that
Everything's positive.
no.
No?
I found that the F1 value is a lot better. So can I do that?
Okay, I will tell you what a fundamental problem with that is. Of course, you can do that. I mean, it's your code. You can do what you want. There's a key issue with what you just said is that you discovered this information by looking at the test set. You discovered that setting the threshold to -1 gives you a good F1 on the test set, right? Which means you're overfitting the test set.
Not only test set, but also a training set.
No, what do you mean? How did you know that setting this to, I'm going to just erase this. How did you know that this is a good prediction rule for a given set of weights?
Because I tested it.
On the test set?
No, also on cross validation.
So that seems funny because that means that you have a biased term
Yes.
and your learning algorithm didn't get it.
Yeah.
So why is that?
I'm still figuring it out.
But in general, you can't use the test set to decide anything of any of these kind of things because then you're overfitting the test set.
I can set a bias like this, right?
You
For
could.
example, without-
But you should come up with that number without looking at the test set. You could, sure. I mean, it is actually done where you train a classifier of this kind, and then you pick a threshold that is not zero, and you find a threshold using another validation set, and you do that if you want to kind of be somewhere at a different place in the precision recall trade-off. That's another way of kind of post-training, kind of correcting your classifier. But for that, you need to do that using a validation set. You can't do that using a test set. Does that make sense?
Sorry, you mean I cannot do that on the test set?
You cannot do that. You cannot, let's say instead of -1, -1 is just a number. Let's say it's some alpha, some number. Can you tell me what's a good value of alpha? Let's say I give you a new data set. Okay? Can you come up with a good value of alpha? No, I mean it depends on the data, right? So now which data are you going to consider to come up with that value of alpha? It could be that you looked at the training set. But if you looked at the training set, what are you doing that the learning algorithm did not? So something funny is going on, right? That's one possibility. It could be that you trained your classifier on the training set, and after the weights are fixed, you had another completely different set, the validation set, that you used to find an alpha. Okay? That's totally fine. And in fact, it's done pretty often where suppose, to answer the question that came up earlier, suppose you are at a point in the precision trade-off, precision recall trade-off where that doesn't work for you, for your application. And you want to change it without actually doing something heavy, like, thinking too hard. What you do is you use a validation set to change the alpha so that it makes fewer positive or more positive predictions. But you should use the validation set. Option number 3 is you can use the test set to come up with the alpha. You have a training set, you train the alpha, you use a test set to come up with the alpha. And then it works fantastically on the test set. But that's not good because you use the test set. Right? So that's what I was doing. Yes.
So I had the same problem that those guys were mentioning where they kept doing a lot of negative ones. So what I did was I moved the C to be attached to the regularizer term instead of the loss term.
Okay.
So is that valid?
Okay, let me write down what you did. Okay. So what we saw in class was minimize over W of C times, I'm just going to call this loss. B is the data set. So this is the whole thing. I'm not going to write what was. This is what we saw in class. What you suggested is minimize over W. Is this right? Is this what you did?
Yeah.
So now C is a constant. It can what I could do is instead of I'm going to write this in a different color. Let's say I write this in black. The same thing I could say this is C times half W times W plus 1 over C. Right? I am minimizing over W. Now C is a constant, and it's a positive number. So I could totally get rid of this, and this minimization problem is going to give me the same thing.
Yeah.
Which means the C that you used is actually, when you attach the C here, it's exactly as if you attached a 1 over C on the other side.
But this way I don't edit your numbers.
Oh, so the numbers that I gave, think of them as guidelines or suggestions. So what that suggests really is that the range of C's that I gave is actually not really good. Right? So for example, as a hypothetical, let's say you solve this problem and the best C that you found, do you have any idea of what the best C was?
It was like, I think it was to the -3.
So 10 power minus 3.
Yeah.
That means this 1 over C, the best 1 over C is 10 power 3.
Yeah.
That means this best thing, maybe 10 power 3 is a good number. So, announcement to the class, try 10 power 3 as your C. For cross validation, at least there's one instance where it seems to be better. Does that make sense?
Yeah.
So yeah, I mean, in fact, in logistic regression, in the version that we saw in class, the hyperparameter is attached to the W. It's 1 over sigma square attached to the W. So there I did. Except they have, increasing, instead of calling this C, let's call this C1. Increasing C1 has the same effect as decreasing C on top. So yes, in fact, there are some versions of SVM where the version, that's right. So it's basically the convince me that what I gave you was wrong. The set of hyperparameter choices, somebody has to decide. What do I know? Right? So convince me what I did was wrong by showing me cross-validation numbers. Don't just say that, I like C equals 17 because today is Tuesday. Show me cross-validation numbers. At this point, we need to be more rigorous about why you prefer a certain hyperparameter. And the rigorous answer is cross-validation. So if you can convince me that a certain C is good, I'm willing to be convinced. Other questions? Yes?
So, we used to choose of that's 5, 3, or something. The maximum I have is 10.
So what happens after 10?
Is whenever I run the experiment, it just stops at close to 200 feet. I'm running it on each less than 8.
You mean it's running out of time?
Not technically, I don't know what. Sometimes it's huge, and some other times it's
Kid kills processes if it takes a food.
Oh, I see. So, so the question is, you feel like the hyperparameter choices that are given for the tree depth is too large.
Yeah, because they're sparse, and then technically.
Okay, yeah. Are you using hash maps or are you using dictionaries? And still it's okay. So once again, same answer. If you feel like a certain hyperparameter choice is terrible, convince me it's wrong. In this case, your explanation is it is so slow that it can't kill it, right? What you need to do then is do some back of the envelope math for how long you think it will take. If you can convince me that it's if only Kate let you run processes for 17 hours, you will get it, but it doesn't, Kate is evil. So just do the math. I'm willing to be convinced as long as there is any rigorous argument. Any other questions about homework? If not, we're going to, start the class. One other announcement, class projects are due on the 14th. Just a quick thing about what needs to be submitted. Most of you, almost all of you will end up submitting code as zip files, but please don't submit data because I don't want to break Canvas. You also need to submit a project report. This information is on the class website, but the report should be no more than 6 pages, and think of it like a short research paper. You should talk about what you did. Why is it interesting from a machine learning point of view, or maybe more even more than machine learning point of view? What ideas you explored, what ideas from the class you used, and honestly, the goal of this project is for you to convince me that you learned something from the class, and in a somewhat relatively unstructured problem. So talk about what you learned and explain the results. Show me the results that you have. Almost all of you are doing empirical work. So it will be results in form of tables and graphs and such things, the kind that you've been doing the homework anyway. And if you had more time or if you had more CPU, what would you do? Yeah.
So the submissions that we turn in, do they have to run on Git?
I would like them to run on Git.
If they don't, should we just attach like maybe like a dump from whatever server we ran on?
Sure.
Is that good?
And for Kaggle, of course, you have to have submissions on Kaggle as well. We've spoken about this. There's a document on Canvas that describes what this is. In your report, please mention which Kaggle submissions should be considered. There should be at least 6 different runs. So someone mentioned that there is an ID or something. Yeah.
So we can't send the ID.
You can or cannot?
We
Cannot. Okay, then give me a date that you submitted it, a timestamp or something. Some way for me to read it and understand this is the one that I need to look at. Any other questions? So one thing I'm planning to try is, I already did this once around the time your intermediate status report was due, but at the end of the semester, I will take all your Kaggle submissions, everything that is not a dummy, and build a big ensemble out of it. Because I'm just curious to see if an ensemble of about 120 projects times 6 would be better than the best. We'll see. Yeah.
For the submission Kaggle, for example, if we have the same algorithm just as perceptron,
Right.
with different transformations, so
They count as different.
count different.
Yeah.
Not one.
Yes. Different transformations count as different, but different hyperparameters don't.
Yeah.
Right. So the way I count something as different is if you have, if the function changes, it's different. If the algorithm changes, it's different. A feature transformation changes the hypothesis space, so it's different.
So you don't need our code for the Kaggle project?
I need your code for the Kaggle project. What was the second one?
I have another. So the question is basically cross validation with cross validation without cross validation, are they different or are they the same?
Without cross validation does not exist. I don't know how you got your hyperparameters otherwise. So there is nothing without cross validation.
Can we change our previous submission in the final one?
I don't know if Kaggle allows you to change it. I mean, you want to count something else. Yeah, sure. Yeah.
Just to clarify, we don't, our code will not be needed to be run on big machines, right?
I would like it to run on Kate, but if not, you can at least show me, upload your run logs to correspond to the thing, if you have that.
So we use, the packages that are not installed in big machine.
Yeah, but here's the thing. I want to know that you wrote the code.
Okay.
And I want to know that you did not use a machine learning library. Right.
You don't want us to submit data, but what about data transformations where it depends on how you want to
Would the data transformations be generated by some code?
Okay, so we need to actually make that code also runnable by.
Or at least inspectable.
Okay.
And kind of, don't make it like spaghetti where I have to be chasing pointers all around, but at least make it readable.
I have a cross-validation question. So when you get the best classifier from cross-validation, do you train another classifier with those parameters and then run it on the test set, or do you use the same classifier that did the best score?
So what you do is you train a classifier, you got your best cross-validation. So cross-validation is a procedure that does not give you classifiers. Cross-validation is the procedure that gives you hyperparameters.
Okay.
You don't get a classifier. You just get it tells you this hyperparameter has this much value. In fact, cross-validation is not even a procedure that says this is the best hyperparameter. It just says this particular hyperparameter choice has this value. You do that for different hyperparameter choices. At the end, you still have only a ranked list of hyperparameters. And you need to pick the best and train it on the full data set. Yeah?
So we accept this kind of Kaggle submission with low accuracy.
It depends on low.
Yes.
If it is embarrassing, I won't. I don't know what low is. Given that I have enough statistics from so many people, I will be able to get a good guess of how well a decision tree would do. So I can compare to that. If, for example, or I can write my own decision tree and see how well it does. And if your numbers are, say, more, really off from that, then I'll take away points. But if the algorithm itself is bad, if the algorithm itself is not doing well, like for example, on the Kaggle data set, decision trees don't seem to do particularly. What can you do? If that's low, that's what it is. So I will compare to the what I expect for that algorithm. Yes.
So speaking of embarrassingly low accuracy, I had probably an error in one of my algorithms while I was running it on the Kaggle test set, and I got 13% accuracy. So I turned it around, and it got 87. Is that valid? Is that legal? Is that like, say you did that in the real world, would people be like, "What the hell are you doing?"
Let's talk about this in the next lecture.
Okay.
Because I do want to talk about the ethics of machine learning. All right. I want to actually start the lecture. We are more than halfway into the class. I want to talk about neural networks. But this was good conversation because this is the kind of practical stuff that you don't maybe get to see in a lecture. So we've seen neural networks. We've seen what they are. We've seen how to make predictions with them. We've seen how to train them. We saw the backpropagation algorithm in the last lecture. So it turns out that there are many, many practical issues that we have to deal with when we deal with neural networks. Because there are so many moving parts that you can't really do cross-validation over everything. Moreover, the learning problem is no longer convex, so the guarantees that come with convex optimization no longer exist. So a lot of other things need to, the practical issues become important. There are many practical issues. I'm only going to talk about a few things. SGD is no longer the greatest thing around because of non-convexity issues, and I'll talk about how we can address some of these problems. Neural networks tend to overfit if you are not careful because they can be arbitrarily expressive. So I'll talk about addressing overfitting, and the other thing I'll talk about, which is kind of related, is the number of hidden layers and the width and the depth of networks. So the bad news is that there is no guarantee of convergence. Meaning there is the loss function that you are optimizing may, for example, look like something like this. And if you start here, you end up here. If you start here, you end up here. If you start here, you end up here. But really the best one requires you to have started inside this little valley. So what can you do? In practice, I don't know why realistic problems, large networks seem to converge when you have tons of data. But you should always keep in mind that stochastic gradient descent or any gradient-based methods that we see in you may see even not just in the class but outside, is they only come with guarantees of being able to get to the local minimum. We don't have the ability to get to the global minimum of the incredibly non-convex functions. In practice also, you might need to train for tens, thousands, maybe, I don't know, of epochs over the data. And the data sets themselves may be massive. For example, a data set that my student has been playing with has about 500,000 examples, and he runs maybe about 300 epochs on them. This is for every single thing, every single cross-validation. So, the running experiments on these systems might take weeks, months maybe, which is why it pays to become good at, understand the hardware you're working with. Like GPUs seem to be doing a good thing. It pays to use good libraries, and if you don't care about those things, it pays to use good code. Another thing that can be problematic is when do you stop? I mean, maybe for this data set 300 epochs is a good thing, maybe for this data set 3000 epochs is a good thing, or maybe something in between. How do you know when to stop? The answer is never really clear. There are, in practice, maybe a few ideas seem to be prevalent, and I'm going to just tell you what they are. One of them is you keep track of the loss, the training loss, and you stop when the change in the training loss between epochs has become smaller than some fixed predefined threshold. Usually it's a relative change, let's say. That's one possibility. Another possibility is you have a validation set, you keep measuring accuracy or error on that validation set, and this is what you did for your first homework actually for Perceptron. How many epochs did you pick? You measured the number of epochs from your validation set that was the best thing. And this tends to be like the most common thing to do, where you have a validation set and you measure your classifier on the validation set at the end of each epoch, and you train all the way to maybe 3000 epochs, but then you go back and take the classifier that had the lowest validation error, which means you need to kind of serialize or save all the models along the way, and this becomes a pretty nasty software engineering problem. The other thing that I think is important to do is you can't just start with one set of random initializations and let it run to the end. You need to check or verify that your learning is robust. In practice, what you could do is you do the same process of training multiple times with multiple random initializations, and then you get many different classifiers. At that point, you have a way of picking the best classifier or somehow combining them, and that's where ensembling becomes, it comes back. The idea of ensembling shows up. So you could ensemble all these things, or you could take the best classifier according to what metric? According to the same things that we use for termination. So it could be training set loss, it could be the error on a validation set or something like that. Questions? This is just all about essentially number of epochs and initialization.
If you have a huge data set, is it valid to just take a smaller distribution of that and kind of do some tests on that to get an idea?
You could. Your initial probes could be done with a smaller distribution, but you should be careful with that, because maybe the effect you're looking for, the concept that you're learning, needs all the data to stick. So maybe any signal that you get from a very, very small subset may not be representative. So you have to think about how much of the data is representative enough. I came up with just yesterday I had this instance where another student of mine, we were working on some problem that where the training set has like I think 1 million examples, and it's getting tedious to try out ideas. So a few months ago we came up with a toy data set which had some of the same characteristics with 8 examples, and we kept probing things. Now we have exhausted the kind of things we can probe with 8 examples, so we now need to go back to the million things, and now we are in a position where we need to do some probes, but we can't use the 8. So it's this awkward thing where we have to do a lot of compute. So and one way or another, you're going to have a lot of compute heavy work. And in fact, this is the reason why, because training is expensive, is one of the reasons why there's a lot of interest in building hardware accelerators just for machine learning. Google's invested heavily, for example, in what it calls the tensor processing unit. I don't know if it's invested heavily in building it, but definitely in advertising it. Alright, another problem is overfitting. Neural networks, as I said, are prone to overfitting. You could end up overtraining because you just ran too many epochs. Like I said, you should hold a validation set out and test accuracy at the end of each epoch, and be prepared to not use the classifiers that are much later in the training if the accuracy is lower. this is what I said. Use k-fold cross validation. Validation, keeping data out for validation means that you've lost some data for training. So you could do cross validation, but once again, be aware that cross validation is computationally heavy, and this is where once again it becomes a bit of an art of deciding how much data to send where, and it tends to be something that you need to decide based on how much data you have. Yeah.
When you hold out a validation set, isn't there a possibility that it will be non-representative of the test data?
You need to sample the validation set in a way that it is statistically similar to the training set. So, for example, if your training set has like your homework thing, let's say your training set has 80% positives and 80% negative and 20% positive, you need to sample your validation set so that it has the same ratios and things like that. That's called stratified sampling. You need to do that even for cross-validation. Any other questions? One important idea that kind of came to existence very recently, and it's in some sense a child of the neural network way of life, is called dropout. Pretty much most neural networks that are trained today use what is called dropout for preventing overfitting, and it's a rather simple idea at the heart of it. A neural network has many layers, right? There are many neurons in the network. What you do is you introduce a new hyperparameter, P, which called, what did I do here, delete? Okay, so let's say the delete probability is P. When you're doing the forward pass during training, so remember, training a neural network has a forward pass where you make predictions and a backward pass which corrects the weight. When you do the forward pass, for every node in the network, independently with probability P, you pretend that that node is deleted. Basically, today's GPU code allows you to do this operation efficiently, where you mask out certain nodes. So you pretend that that node doesn't exist, which means all the, not node, let's say the node doesn't exist, and that means all its outgoing information is lost, meaning the outgoing weights are not going to play a role. And you just pretend the node doesn't exist, you make a prediction. Which means what you're expecting is all the nodes that are not deleted to do the heavy lifting. You're hoping that the prediction can be made using only all the nodes that are not deleted, and then you do backpropagation, you update only the edges associated with those nodes. Right? And you repeat that. Every time you pick a new example inside your gradient optimization, you randomize this mask essentially, because you randomly delete nodes. Yeah?
So deleting means like sending 0 out from that node, or what?
Deleting means you pretend that you have a computation graph where that node never existed. Effectively, that means that it's a 0. Yeah. The output of that thing gets multiplied by a 0. Essentially, what this there's a lot of efforts to understand why this works. So this idea was introduced in a paper by Hinton and others in 2012, and it works. It works fantastically well, and since then there's been this scramble of attempts to explain why it works. I personally like two explanations. There was a very interesting paper from I think 2013 or 14, which pointed out that at least in certain classes of networks, in particular they analyzed I think linear models even, it turns out dropout is mathematically equivalent to a very special kind of a regularizer. So essentially dropout is a kind of a regularizer. Another perspective on this, which also is kind of, it shares some intuition, is that you can think of this as every time you delete some nodes, you get a new neural network. Right? You get a different neural network, a different hypothesis space, and what this process of dropout and randomly dropping out nodes is doing is it's averaging all these minor perturbations in the model space, and it has this ensembling effect, similar to like average perceptron if you want. It has this sort of a soft ensembling effect, and that's why it's leading to generalization. One way or another, dropout works. Most neural network libraries today give you easy way of introducing dropout. Invariably, you have to pick one number. Some libraries call it the delete probability, some libraries call it the heap probability, which is like 1 minus that. One way or another, you have an extra hyperparameter that basically gives you, leads to better generalization. Yes?
So after dropping out, will it relearn the weights or will it use the previous weights?
Say that again, after dropping out?
So let's say it drops out a few nodes.
Yeah.
Will it relearn the weights in that layer or?
Oh, it will. So let's take this picture. So we have this node 1, 4 and 5 have been dropped out. Let's say this edge goes out from 1 to this thing here. This weight is not touched in this update. Basically what this means is that weight is kept frozen in that update. This weight is updated. The next iteration, let's say, the weight associated with edge node number 2 is, node number 2 is fake deleted. That means the edge associated with node 2 will not be changed. The edge associated with node 1 would use the value from before. So the values are kept. Essentially, there's a mask that's put in the on the weights so that those weights are, it's as if those weights don't exist. And the next time you show up, next time an example shows up, the mask might be different, so the previous weight exists.
Could it be thought of as enforcing like an ensemble kind of property of the neural network, so that no certain neuron is too strong, too specialized to?
That's exactly, that was the intuition that was used to come up with the idea that no single neuron or no set of neurons are totally required to make the prediction, and that way you kind of force everything to kind of keep up. So this is very common, and if you want an interesting set of research questions, it's thinking about formalizing dropout and making formal connections to regularization and such things. Let's talk about the number of hidden units. With neural networks, you run the risk of having too many hidden units or too few hidden units, or too many hidden layers and too few hidden layers. And all of these can lead to underfitting or overfitting. If you have too few, you can lead to underfitting. Too many can lead to overfitting. And basically, cross-validation methods can be used for deciding the number of layers and the number of units and such things. This is why some people are skeptical of some claims made by neural networks because it's essentially unreplicable. If Google claims that they have a translation engine that is better than the best human expert, how can you independently verify that? Because there's only one instance of that data, maybe Google's data set, and there's only one, maybe 3 or 4 organizations on the planet that can actually repeat that experiment because it requires so much computation. So I don't have a punchline there. That's pretty much it. So yeah.
So question. So the architecture is also a hyperparameter?
Yeah, this is the architecture. Right? The architecture is the layout and the number of nodes and all these things. So you can think of the architecture as a hyperparameter. Yeah.
I just want to make sure I'm thinking about the previous slide correctly, where you're dropping out. So that's changing the architecture, essentially.
On the fly.
On the fly.
Yes.
Yep.
That's an interesting way of thinking about it. I've not thought of it that way, but yeah. You're changing the architecture for that example. And then bringing back the change, undoing the change for the next example. Yeah. Okay, so I'm going to start wrapping up the neural network part of this class. What we saw was just a very, very high-level introduction to neural networks. Neural networks are essentially probably best thought as computation graphs with multiple layers. And the reason why they exist and why they're popular is because they answer this question of where do the features come from? What is a good representation that is needed to train this particular concept? And the answer from the neural network universe is the best representation is the one that's learned. So why ask a designer of the problem to come up with features when we can convert that into a learning problem? invariably, in order to do that, you need a highly expressive class of models. And one question to think about is whether this is always a good thing or not. It's possible to easily overfit, so you should be aware of that. Neural networks are here to stay. They are perhaps one of the most, well, I say that as if they're new. They've been around forever. They are here to stay again. The difference this time, it seems, is like we have a lot of data, a lot of compute, so we can actually explore the space of models maybe more effectively. And this space exploration is facilitated through this algorithm that we saw, backpropagation. Backpropagation, at the heart of it, is essentially nothing fancy. It's just a mechanized way of computing derivatives. So it's not if you want to be pedantic about it, backpropagation is not a learning algorithm. Backpropagation is just a tiny subcomponent inside a learning algorithm which lets you compute gradients. You can plug it into other learning algorithms, in particular something like stochastic gradient descent. It's a hugely impactful area of research, but it's also really fast moving. There is, new papers seem to be coming out about neural networks that if you read them, take them at face value, every new paper invalidates everything else that came before. Of course, that's not true. But there are a lot of new ideas and new algorithms that are coming out in the space. Some ideas that you might hear about, momentum and AdaGrad and AdaDelta and Adam. And there are a few variants. Today, for example, when my students train neural networks, I ask them to use Adam, partly because it seems to work, and it's essentially stochastic gradient descent on steroids, with a lot more bells and whistles that make it better behaved in some sense. And also there are efficient implementations of these things. We also did not see any named neural networks. There are tons of them. You might hear about restricted Boltzmann machines or convolutional networks or recurrent neural networks or long short-term memories and all these things. We didn't see any of that. But hopefully, you have the tools to kind of pick up on this and, this sets you up to understand what's going on or what questions to ask. There are a few neural networks classes next semester. Maybe you can pick up on these names when you see them. Yeah?
I wanted to ask, what's the difference between process and yours?
So this is about next semester, right? My class will be about language, he'll be talking about vision. Images. Yeah. Which means that, interestingly, this class of networks, convolutional networks, seem to be the thing to do when you're doing vision. Recurrent networks seem to be the thing to do when you're dealing with languages. And they seem to have, there are interesting sub-architecture choices that show up here within each of these communities that don't directly transfer to the other. So there's, anyway, the application is different. The focus will be on the application in both cases. All right. Yes.
So named neural networks, does this mean that's a specific architecture?
Yeah, they're classes of architecture.
Okay.
Yeah. Mostly. Almost mostly. For example, restricted Boltzmann machines and autoencoders also came with a certain way of learning. But I don't think people use that stuff too much.
Do you have any practical advice when we're reading like papers about new
be skeptical.
architectures?
Be skeptical.
Yeah.
When you're reading new papers about these things, it can be overwhelming. And the way to get around it is to read more. Because you will realize the same thing keeps coming up again and again. And then you start modularizing things. Okay, this class of ideas comes from this thing. It works because it seems to have worked in these 18 papers. So that's not the novelty here. Also try to look for surveys before you read the papers. There are very, very good surveys of these things. I strongly recommend this book by Ian Goodfellow and others on deep neural networks. That gives a very good survey of this field. For the NLP part of it, Joachim Goldberg has written a book on recurrent networks. It's fantastic. Most of these books are available online for free if you're within the university network. So that's another good thing. I saw another hand. Yeah.
Just a quick question on neural networks. Too many hidden units leads to underfitting or
overfitting. Because very, very loosely, think of it this way. Too many hidden units corresponds to too many weights. Right? More weights. More weights corresponds to more VC dimension. The VC dimension of a neural network is roughly, it increases as the number of edges in the graph grows. So it can lead to Alright, I'm going to switch gears now. We have 15 minutes, maybe that should be enough. I'm going to move from neural networks to another topic whose only connection to neural networks is the fact that it's also nearest neighbors. Nearest neighbors might be the easiest classifier you will see. It's a classifier that you could have invented without taking this class, and it keeps getting invented again and again. I'll talk about k-nearest neighbors, the classification problem, or what the classifier is. And let's see if you have time, maybe I'll talk about Voronoi diagrams, and I don't want to inflict the curse of dimensionality on you in the last lecture, so maybe I'll end up skipping that this semester. But it's actually something very cool, and if you're interested, you should totally take a look at, read about the curse of dimensionality. It's something that will leave you feeling a little bit uncomfortable. If you like that kind of stuff. Who doesn't? Alright, so let's talk about k-nearest neighbors. I'll talk about the basic algorithm first. So the task looks like, or you can set this up in this way. Let's say you have some points in space. Some of them are colored blue, some of them are colored red, and there are these 3 points A, B, and C. And let's say I come to you and ask you, how do you color them? What's the color for A? Blue. What about B? Somebody said green.
I mean, maybe.
Yeah, sure. Let's assume that there is some regularity in the universe. What would you say is the color for
red?
Red. And what about C?
Red.
What classifier did you use?
You choose the one that's closest.
You essentially use nearest neighbors. You pick the one that's closest, and if you based the color on the nearest neighbors, or the color for any point is based on what you think the color for that region should be, and the color for the region is the color of all the points in that region. You essentially implicitly used a nearest neighbors algorithm. What you did, and maybe or maybe not, what you did do is you separated the entire region into blue and red, and you said, yeah, this point is blue because it's in the blue region. And maybe this point here at the top is blue because it's in the region, but it's very close to a lot of red. And this one is also red, but it is kind of close. So you think about it this way: if you get a bunch of points in the space that are labeled with some colors, every point in the space, every single point in the space, should be nearest to some other point in your set, right? This point is closest to this point is close to this point is close to that. Every point is close to one of your training points, which means, and if you use this rule that the color of a point is the color of the closest point, that means you've basically colored the entire space. That's the idea behind the nearest neighbors classifier. The simplest version looks like this. Let's say you have some features and some labels, you have some training set. The features could be, spam and, you know what this is. The learning algorithm for nearest neighbors is not particularly hard. You read the data and you store it somewhere. That's it. You store it in a database. That's it. Literally, remembering the training data is the learning algorithm. All the heavy work happens when prediction's done. When you're predicting, when a new example comes in, you go over your entire training set and find that one point that's closest to your new test example, You look up its label and you say the label is that. That's what you did, right, for this example that we just saw. That's pretty much the entire algorithm. You know, for classification, let's get to classification in a bit. K-nearest neighbors is a slight generalization of this idea where you don't want to pick the one closest point, you want to find the k closest point. You want to find the points in the space, k points in space that are closest to the test example that you have. And you construct the label for this new example using all the labels for these k neighbors. How do you do that for classification? So let's say you have k closest points and yeah.
Weight them by how close they are.
You could weight them by how close they are, but if you don't want to implement all this weighting business, you could just vote, have them vote. So you just take the majority label. So there are, you could predict the most frequent label among the neighbors, and that's basically your k nearest neighbors classifier. If you had to do regression, remember in regression, every point, the label is a real number. So you have k neighbors, you have k real numbers, and you have to convert them into those k numbers into a single one. What would you do? Average. That's it. So basically, this is pretty much all there is to say about k nearest neighbors. If all you need is to know what they are. K nearest neighbors are a class of methods that are called instance-based learning methods, where learning typically involves storing the entire training set, and prediction